So let's discuss about the effective spring constant of two springs connected in series. Suppose you have two springs like this, the spring 1 and another spring, both are connected in series. Let K1 be the spring constant of the first spring and K2 be the spring constant of the second spring. One end of the first spring is connected to one end of the another spring. So this connection is called the series connection. Now, if you, let's call this point, let's just name all the points. Let's say the point here is P. Let's take the point at the end of first spring as A and that of the second spring as B. Now, if you apply a force at the point P on this combination, so both the springs will get stretched like this. There is extension on both the springs. Suppose if you apply a force in the horizontal direction, let F be the amount of force. Now, if you look at the extension in the first spring, the first spring is extended this much. Now the point A is here. Clear? So A is here. So the extension produced is x1. Let's take that as x1. Similarly, for the second spring, this point is now here, B. This point B is now here. B is now here. So the extension produced is x2. Clear? Now, since the connection is series, the force on both the springs remains the same. So the force acting on the first spring is F. Also, the force acting on the second spring is also F. And if you apply Hooke's law, we have force is equal to Kx. This is the Hooke's law. So for the first spring, F is equal to K1. The extension produced in the first spring is x1, implies x1 is equal to F divided by K1. Let's call that as equation number 1. Now, if you apply Hooke's law on the second spring, F is equal to K2 x2, since the extension on the second spring is x2. Therefore, x2 is equal to F divided by K2. Let's call that as equation number 2. And the total extension in the spring, let's say x is equal to x1 plus x2. That is, x is equal to, that is a total extension means the extension in the first spring plus extension in the second spring. So x is equal to x1 equal to F by K1 plus x2 equal to F by K2. Let's call that as equation number 3. Now let's replace these two springs with a single spring like this. Let's Ks be the spring constant of that single spring. And if you extend this spring, this new spring, with the same force we applied before, and if the extension is x, let the extension produced in the single spring be x. So what basically this means? This means you can replace these two springs with a single spring of effective spring constant Ks. That is, you can substitute the activity done by these two springs can be replaced by the activity of this single spring. So that's meant by the effective spring constant. So here, if you apply the Hooke's law, we have F is equal to Ks into x, or x is equal to F divided by Ks. Let's call that as equation number 4. Clear? And if you compare 3 and 4, you have if you compare 3 and 4, we can write x F by Ks instead of X. That is F by Ks equal to, substitute this value in here, equal to F by K1 plus F by K2. So this is equal to F by Ks is equal to F into 1 by K1 plus 1 by K2. You can cancel this F. So 1 by Ks equal to, you can cross multiply this, K2 plus K1 divided by K1 K2, or taking the reciprocal on both sides, we have Ks is equal to K1 K2 divided by K2 plus K1, or Ks is equal to K1 K2 divided by K1 plus K2, which means if you take a spring of spring constant K1 K2 by K1 plus K2, then you can replace these two springs with that single spring. Clear? The effect produced by these two springs can be replaced by this single spring. Clear?